Here is the real life operation of the float arm. This is an old float arm, so there are some dead spots. It's sat out in the atmosphere for a long time and it's got a bit corroded, but you can generally see the complete operation here from min to max. Interesting to note that at the low spot here, that sits about, it's 12 millimeters before we actually start to detect anything moving. There's actually a gap of about 5 or 6 millimeters between the base of the internal compartment and the float. So this sits directly on the fuel tank base inside under spring pressure, and then as the fuel level rises, your float level rises, and that comes to the absolute maximum. Been for a short trip. You can see the live plot of the fuel tank pressure sensor. We've come to a stop. I'm going to try just driving a little bit. Difficult to, the sunlight is affecting things. Anyway, that's the result of the journey. The small dotted line, the thinner line, is the actual pressure sensor value, which is obviously changing, and the thicker line is the actual inches of mercury. So that should give us something to work with. Here is the vacuum sensor, or fuel tank pressure sensor, or vapor sensor, goes by several names. And this particular sensor is used in a lot of vehicles. It's used in Hummers 2003 to 2007. I think 2008, 2009 may use a different sensor. To show how it operates, I've hooked it up to a power supply which is set for 5 volts, which is this value here. The scope on the right there is measuring the signal voltage. The meter on the left here is measuring the current going through the device. So on the left hand side, on the orange wire, we've got 5 volts. The middle wire, red wire, is the signal, and the black wire on the end there is 0 volts or ground or chassis. There's a port on the back there which connects via a rubber grommet, which I think when you buy them they come as a pair. You get a grommet and this at the same time, and that just pushes in either into the tank or into the fuel pump. The reading on the right at the moment is measuring the ambient tap pressure. You will see that as the pressure goes down, then the voltage will go up, and when the pressure goes up, the voltage will go down. So it's kind of upside down really, it's the inverse. To show it operating, which is very difficult to actually do in vehicle, I've got a miniature Hummer H2 fuel tank to simulate what goes on. So we just stick that pipe on the sensor, which is hard to do with actually changing anything. If I squeeze the tank, which is creating positive pressure, you'll see that the voltage goes down. I'm hardly pressing that at all. These are very small readings, and I'm going to try and convert these on screen for you in pounds per square inch, which I think is what most people are used to dealing with, instead of inches of water. If I let it go again, it returns to whatever pressure was left in the system. If I unplug the tank, which is easiest done on this end, and then squeeze it to create a vacuum and let go, you can see that the voltage now goes pretty much up to maximum. Above 4.9 is considered a fault and will be reported as a DTC code, and similarly below 0.1 is also considered a fault and you'll get a DTC. So that sets the opposite operating range. 1.5 volts is normal atmospheric pressure, I believe. This will be below 15 pounds per psi. That's what atmospheric will be. So you can see the pressure is quite high here today, and we are, as you go up in altitude, the pressure will go down. So all of these things are affected by altitude and pressure. So that's how that sensor operates. Quite simple and very sensitive, I have to say. Here I've hooked up the fuel pump motor to a bench power supply. These connectors just plug in. This connector was the one that actually sat in the top there, which I've removed. You can just see the hole that it mounted in here. That was the hole there. So I've taken that out. That is pushed in. It's pretty hard to pull out, particularly if your fuel pump is rusty like this one. I've connected it up. I've set the power supply to 12 volts. I'm just going to turn it on and we're going to see what current it takes. I must point out there is no fluid in the reservoir on this, and so this pump may be not straining too much. I have no idea what the actual current will go up to when it's actually pumping around real fluid. It could well be double. As it stands with no fluid in the reservoir, we're taking about 1.2 amps. And this pump sounds a little bit ropey to me. It's probably because it's been stood in the atmosphere for quite some time, well over 2 years, and it's probably dried out and the bearings are dry. And just bearing in mind that this pump actually operates submerged in fuel. So all these electrical connections and everything are all in fuel, including the float sensor. It's all submerged in fuel. One final thing on the fuel pump motor. I've got a multimeter here set on ohms. The probes have been zeroed out, so it should read 0 ohms, and we can now measure the resistance of the fuel pump. Bearing in mind this is not a proper test because once it starts up the dynamics change, but you can see with no energy connected to the motor we're registering half an ohm, so it's very low impedance. You would infer from that that at 12 volts that'd be like 24 amps, so that would be a lot, but I don't think it's going to be that much. But this is for reference, so if you wanted to measure your fuel pump to see if it was wiring correctly or no breaks in the wiring, then you should be seeing quite a low resistance like this without any power connected. That's with the leads going into the terminal on the top of the pump. Whilst I have the pump apart, you can see here is the SOC filter, which looks a little bit like my CAD model, and you can see that clips into over the motor and locks it into place. I'm going to see if I can just unclip this. Might be able to do it, I don't know. This pipe's attached to the top, but we'll see if we can get it to come out. That's one half. So there's the other half. So that's the SOC filter. You can see, as I mentioned before, this is probably well rusty because it's been stood out in the atmosphere. And normally this is submerged or well soaked in fuel. What the state is internally on this, I'm not sure. Maybe one day I'll cut it open and have a look. Alright, I've managed to get the filter past these 4 clips. It took several screwdrivers and some thin steel rules to actually get it past, but it just come out. Again, this is not a service replaceable item, and you can see it's probably not cost effective. On the end of the fuel filter is the pressure regulator, which I can release. So that's the pressure regulator assembly. That itself is a clip-in item. I'll talk about that in a minute. There's the fuel feed in, which is this line here. It's tricky. So there we have the fuel feed, which is bonded to the pipe that's in the top there. And there is the fuel filter, which looks exactly like the CAD model, and you can see internally in here are the O-rings for the seals. There's one in every port, so there are 3 altogether, 3 O-rings which seal. Again, there's something loose inside there. It could be interesting. Maybe I will cut this open and have a look at the end when we're done. One interesting thing in the actual internal frame is there's a metal tag. Can you see that there? What that does is it grounds the motor and the filter together. I suspect it's to stop the risk of any kind of spark between the two. So now we come on to the pressure regulator, which I'll try and get out. Alright, I've managed to release the regulator. Now I have to confess I don't understand what the internal arrangement actually looks like. I've only got my interpretation of what it is. I seem to be missing something. Oh yes. There's an O-ring, a large blue O-ring which is inside, which sits over there, like that, to form a seal. And then inside this housing is a mesh filter. And what happens is, fuel comes in from the filter through this port here, circles around inside there, so it goes around this kind of cavity here, and it's forced through this mesh filter into the pressure regulator. Then inside the pressure regulator is a pipe which presses against the diaphragm. You can feel the diaphragm inside, and the spring tension of that diaphragm is controlled by this screw. But anyway, there's a spring inside, and as soon as the required pressure is being reached, fuel starts to come out down the center of this tube, and that feeds into the cavity in here, goes down, goes around inside, and it comes back up through these holes and ports inside here. So that's how that pressure regulator works. Now this is very similar in shape and size to the one that's on the 2003, which is external. I would imagine they're going to be similar pressures. This is a closer look at the fuel pump reservoir. You can see that there is a spring in here. The difference between this AC Delco unit and the others is that this spring is internal and not wrapped around the shaft of the actual fuel pump stands. The point is that this stops any chance of any cables getting trapped during the lifetime of the pump, so this is held internally. What that spring does is ensures that the base of the reservoir is always in contact with the bottom of the tank. Obviously the tank can expand slightly and the fuel sloshing around. It's important that this is datumed against the bottom of the tank at all times. So that's what that spring does. Very important. Also at the bottom of the tank you can see these little one-way valves. There we go. I've taken a valve out. It's just literally a disc with a pip on it. That allows fuel to come in through the base of the reservoir and into the tank. So it's like a trap. It means that fuel can get in but it can't get out. Also the reservoir is this venturi. The venturi is fed down this pipe from the pressure regulator. So you've got fuel going down this tube here under pressure, and it goes straight through this little venturi, and it's very difficult to see. I can probably do a CAD model of this at the same time, but there's a gap between the nozzle of this little pipe here and the reservoir, and what that does is as the fuel is fed back in under pressure, so fuel that's not being fed to the fuel line is being returned back into the pump and sprayed back up this tube here, and as it does so, under venturi effect, it pulls more fuel in, so fuel is coming in through here and back into the reservoir. And then we've got the sender. The sender we looked at earlier, and I didn't point out in that video, but this is a ceramic thick film resistor, and you've got little wipers on here. Now different fuel pump manufacturers will make different claims about the quality of these wipers, whether they've got 1, 2, 3 and what they're made of. So obviously that's quite an important thing, because this is constantly going up and down with the fuel throughout the life of the fuel pump. And you can see it's soldered onto these wires, and this cable just plugs in to the top of the pump. Now this just slides in. It slides in quite easily. These cables get hooked around here, and it just literally clips in. Getting it out, however, is a lot more tricky, as I'm sure you'd like it to be, because you don't want this jumping out when you're driving around. So we'll release the clip this side, right, and then keep holding it, pressing it down, and release the clip on the back, and then it pops out. I'm sure you'll figure it out, it's not difficult. But that's the fuel pump reservoir in essence. Two one-way valves, a venturi at the bottom for the return fuel, and the sender there, which we've discussed in detail earlier on. So what we're left with is the backflow restriction device that's fitted into the lid here. But if we take this little backflow regulator, it stops the fuel from flowing back through the EVAP line. Right, there we go. Then on top of here is a float chamber, and you can see there's a spring inside. So the float is probably designed similar to the sender arm, and you can see this has got this little nitrile seal that goes on the top there. So the idea of that is it pushes against there, and as the fuel floats up, it hits that stop. You've got a counterbalancing spring here just to make it exactly the right pressure, just enough to close that valve off. So that spring goes in there, that rides up and down as it fills up with fluid, which comes in through the base there and then blocks the port off. This has got an O-ring on it which sits inside here, and it's kind of like a dogleg shape that comes out finally through the EVAP line. Test the little backflow valve. I'm just going to try dropping it in as the fuel level rises. You can see it pushes up and stops the valve, which is exactly what it's designed to do. How clever is that? Just to add to this, you can see at the bottom there are two holes. The rate of flow of water is controlled, or fuel in this case is controlled by those holes. So it takes a while for it to fill up. It takes a while for it to go down. That's some kind of damping. I think this being held in probably by meniscus fuel is probably a bit easier to flow than water, but that's what that's for. So everything's designed for a reason. Very clever. Some of these things from GM are extremely clever. When making this video, I was always keen to see what happened to a fuel pump in real life. It's very difficult, obviously, when something's self-contained in a fuel tank, to see what actually happens. So to try and see this, I've got my old fuel pump connected to a bench power supply with the 12 volt positive lead going to the grey wire on the pump, which is reversed to my earlier video, but I wasn't pumping anything, so it really didn't matter. I've got a bowl full of plain water. The fuel line has been doubled back into the bowl. I've got a meter here set to millivolts. There's a 10 amp shunt in here, so it's 100 milliamps for the full 10 amp range. I did try using the meter on its 10 amp range and it blew the fuse, which is hardly surprising. It's quite a surge that takes place when this thing kicks off. So we can see the current being drawn on here. I'll turn it on and we'll get the pump recycling. That flow seems normal compared to the other videos that I've been watching on YouTube. That seems perfectly a reasonable amount of fuel rate. Not to confuse fuel flow with fuel pressure, two different things. To simulate having pressure, I've got a screw which I'm going to screw into the end of that pipe and we'll see what happens. So water can escape around the threads, and this would simulate probably a car not running and the fuel pump is on. So let's just see what happens. And you can see some fuel is coming out through the threads, but you can see the reservoir is now filled up full of fluid, and you could hear the actual pressure regulator kick in. But now just look what's happened to the current. The current has now gone up to 7.5 amps, and that value is probably more in keeping with what happens in real life. At the moment this is kind of like in a reflow mode. This is if your engine isn't running and the fuel has just been totally recycled. Now I think we could change that flow rate by adjusting the pressure regulator on here. It doesn't matter, it's never going to be used again. So if I increase the amount of pressure required to cause the flow, you can see that the current's going up. So that's the effect of the pressure regulator. If we went the other way, you'd watch it go down. So that's quite a spectacular operation of your fuel pump. You can see that the venturi is feeding fluid back into the reservoir, filling it up, and it's just nicely recycling. I'm not going to try unscrewing the screw out while it's running because the pressure surge is amazing. I've got water all over my office space here. It's quite explosive, not to be underestimated. So that is the fuel pump actually running as in real life. I just slackened the screw off and just increased the flow a little bit more there, and I just wanted to see what the actual current was happening. So that's another part to the story on fuel pumps. Quite exciting, I think. Probably worth a whole video just to see this happening. Thank you for watching this video. Please give it a thumbs up, share and subscribe. Oh, and don't forget the alert bell.